Hey everyone, and welcome to this explainer. Today we're going to completely flip how you intuitively grasp the complex physics of classical mechanics. We are talking about collisions. You know, how things crash, bounce, and stick together, and how the universe calculates the aftermath in the literal blink of an eye.
To kick things off, let's look at a totally counterintuitive paradox presented by the legendary physicist Walter Lewin. Just imagine a really heavy bowling ball rolling along and slamming into a stationary, lightweight tennis ball. What actually happens? Well, your gut intuition might tell you the tennis ball just kind of gets pushed along at the bowling ball's speed, but no way. As you'll see, the tiny tennis ball doesn't just match the bowling ball's speed, it absolutely doubles it. So how does that work? Let's figure it out.
Here is our agenda for today. 1. The rules of collisions. 2. The center of mass frame. 3. Graphical diagrams. 4. Paradoxes and applications. And 5. Energy loss.
Let's start with Section 1, the rules of collisions, the ultimate currency of the universe.
Before we get into the clever tricks, we really have to lay down the basic foundation. When objects collide, they basically fall into two main camps, elastic and inelastic. And the vital distinction here is what gets saved and what gets spent. Momentum is strictly conserved across the board. It's basically the universe's ironclad rule. But kinetic energy, now that is a currency that can be kept perfectly intact in elastic collisions, kind of like billiard balls bouncing off each other. Or it can be permanently lost, transformed into heat, sound, or deformation in inelastic collisions, like two cars crumpling in a bad crash.
Moving on to Part 2, the center of mass frame, the physicist's cheat code.
Okay, so we're going to completely change our perspective with a conceptual cheat code called the center of mass frame, or just the C-frame. By definition, this is a moving reference frame tied directly to the center of mass of the colliding objects. Try to imagine you're riding along on a magical, invisible camera that always stays exactly at the balance point between the two colliding bodies. By jumping into this C-frame, the chaotic, moving universe suddenly balances out perfectly. The total momentum of all particles in this frame is always exactly zero.
Just look at the stark contrast here on the screen. In your standard, everyday laboratory frame, calculating an elastic collision involves these incredibly messy fractions with masses and velocities, heavy algebra that is honestly super easy to mess up. But in the C-frame, total momentum is simply zero, and the math for an elastic collision? Practically none. Because the momentum is zero, a perfectly elastic collision simply means the particles just reverse the direction of their speeds. U1 literally just becomes minus U1. It is just absolute elegance.
That brings us to Section 3, mass, momentum, graphical diagrams, solving geometry, not algebra.
So, what if we could take this elegance a step further and solve collisions without a single algebraic equation? What if we could just draw it? Enter physicist Akihiro Ogura's brilliant mass-momentum diagrams. In these, mass sits right on the vertical axis and momentum is on the horizontal axis. Particles before a collision are drawn as simple vectors coming right from the origin. See, point A represents one particle and point B represents the other. You just plot their mass and momentum and boom, you have their physical state right there on the graph.
Now, the absolutely crucial point is how we find that magical center of mass frame geometrically. By simply drawing a diagonal line representing the total system, basically adding the two vectors together, we instantly construct an oblique coordinate axis. You draw parallel lines down to the horizontal axis, and as if by magic, you reveal the center of mass momenta for both particles. Zero math required. And notice how they are naturally, perfectly symmetrical around the origin.
And what happens after the collision? Well, for a perfectly elastic collision, just remember our cheat code. Speeds just reverse in the C-frame. Geometrically, you literally just exchange the momenta symmetrically across that diagonal axis we drew. You draw the dash vectors, and your final velocity states are instantly drawn on the board. You can literally measure the final velocities off the graph without solving a single equation. It's really a stunning visual representation of Newtonian mechanics.
Next up, Section 4, paradoxes and practical examples, testing your intuition.
Armed with our shiny new C-frame toolkit and these intuitive vector diagrams, let's revisit that opening bowling ball paradox and really put our intuition to the test. Why exactly does the tennis ball fly off at twice the speed of the bowling ball? Well, let's use our C-frame cheat code. The bowling ball is so incredibly massive that it practically is the center of mass, so the C-frame is essentially moving at the bowling ball's velocity, v. From the perspective of the bowling ball, the tennis ball is rushing toward it at speed v. When they collide elastically, the tennis ball just reverses direction in that frame, bouncing away at speed v. But wait, To get back to the lab frame, our perspective standing on the ground, we have to add the bowling ball's forward speed back in. So v bounce plus v frame equals exactly 2 times the initial velocity, 2v1. The math is beautifully simple when you just shift your perspective.
We can also apply these rigid rules to the classic ballistic pendulum, which is a brilliant device used to measure the speed of a bullet. Here's how it plays out. 1. The bullet hits a stationary wooden block, a perfectly inelastic collision where momentum is conserved but kinetic energy is lost. 2. The combined bullet and block swing upward. Now mechanical energy is conserved. 3. By simply measuring how high the pendulum swings, we can work backward. We seamlessly shift from energy conservation during the swing to momentum conservation during the crash to calculate that a tiny bullet was traveling at an astonishing 199 meters per second right before impact.
Finally, Section 5, Energy Loss and the Carnot-like Theorem.
For a final concept, let's explore the absolute limit of what happens when kinetic energy is destroyed. Where does it go, and what's the absolute maximum amount we can lose? This brings us to a fascinating concept that functions almost like a Carnot theorem, but for collisions. First, the maximum possible kinetic energy is permanently lost when colliding bodies stick completely together. Second, and this is genuinely mind-blowing, the total energy lost as heat in the lab frame is exactly equal to the system's initial internal kinetic energy calculated within the C-frame. Think of a piece of putty slamming into a concrete wall. In the center of mass frame, they come together and stop completely. 100% of that internal kinetic energy vanishes into deformation and heat. The C-frame immediately tells you the absolute maximum heat a collision can ever generate.
As physicist Walter Lewin so beautifully put it, nature is going to calculate like mad to conserve momentum, to conserve kinetic energy. Whether we as humans use heavy algebra, elegant center of mass frames, or Ogrekov's chalk vectors to figure it out, the universe instantaneously computes these profound conservation laws without breaking a sweat. It just happens, flawlessly, every single time.
To test your newly acquired intuition on exactly how nature calculates, ponder this famous puzzle for next time. In an 8-ball Newton's cradle, if you pull back exactly 2 balls and let them strike the 6 stationary ones, what happens next? Nature calculates, and the only way to conserve both momentum and kinetic energy simultaneously is that exactly 2 balls must pop out the other side. Try to prove it to yourself. Thanks for joining me on this explainer, and keep questioning how the universe works.